Hi friends. So here in this particular session, we'll be looking into one of the very powerful searching algorithms called as the binary search algorithm. So now, this first of all, this is a very powerful searching algorithm, and herein what we will see about is first of all, what is the algorithm, the intuition behind this particular algorithm. Since the name suggests binary search algorithm, so it basically intends to divide the problem space into half as we take the steps forward. And we will discuss shortly as to how this particular algorithm is working out. But here, one of the prerequisites that this particular algorithm needs to suffice is all the elements in the collection over which the searching happens needs to be in a sorted order. So that is one of the prerequisite for this particular algorithm to work. So what does that mean is, so now if we take an example, so let's say we have a list. So we have a list X which has certain elements, 5 elements, 1, 2, 3, 4, and 5. Now these are the 5 elements, and but we need to search out, let's say the value that we need to search, whether this value is there in this particular list. Let's say that is 5. So now how the binary search algorithm works. So here in the first step, what it does is basically, uh, since we know the indexes in the Python. So for that example, so let's say this is a list, so it will have index 1, 0, 1, 2, 3, and 4, right? So it is 0 indexed. So the 0th element is 1, first is say 2, and the second element is 3, third element is 4, and fourth index element is 5. So these are how the indexes are there for the list. So what happens is, so coming back to the step number 1, what it does is, first of all, it initializes the counters. So it has got a start counter. Start is initialized as 0, the initial index, the first index. The end counter is initialized as 4, the last index, which is nothing but the length of the list. The length of the list is, it is having 5 elements, right? So the length of the list is 5. That is 5 minus 1. So that is a 4, that is the last index, which is end index, and it is initialized to the value 4. And now we calculate the middle part, the midmost element. And how is that mid calculated? It is taken as an integer value of start index plus end index divided by 2. So it is the middlemost index of the, or the middlemost place between the start and the end counters. So for the first iteration, what we have is start is 0, end is 4, and mid will be the start value is 0 and the end value is 4 divided by 2, that, and the integer of it, and we take it as int of 2, that becomes 2, right? So we have start is equal to 0, end is equal to 4, and mid is equal to 2. So now with this elements, what we do is, the second step what we do is, sorry, in this particular so what it now does is, this particular algorithm it checks the value, in the particular list at the middle position, which is the mid counter, and for this particular iteration the value of mid is equal to 2. So the value of the index position 2 in the list X will be equal to here, right? So this is the second index here, and the value is 3. So now it checks whether the value to be searched is equal to the X of mid or not. So what we see here is, we have the value which is 5 that we need to search, and we have the mid value 3. So 5 is not equal to 3, but in fact 5 is greater than 3. So now what happens if 5 or the value that we need to search is greater than the value which is in the middle? And since this list is sorted, so what it would indicate is the value is lying towards the right of this particular middle value, right? So we have herein, this is the right portion and this is the left portion to the middle value, right? So it is lying to the right of the middle value. So what it denotes is the problem space now is coming out as, in the second step or in the first step itself, we got an indication. In the first iteration, we got an indication that the value is lying towards the right of middle. So what it does is, this algorithm, what it does is, it assigns the value of start. Since the value 5 is greater than 3, so it will mention start is equal to mid plus 1. That is a one index greater than the middle position. So middle position was 3 and one index greater will be the fourth, right? So now the start index will be pointing to the 4 index position. The end will remain the same because 5 was less than 3. If there would have been a number, for an example 2, which would have been less than 3, then what we would have done is we would have moved the end pointer towards the left or towards the mid minus 1 location. See how intuitively it is that, let's say, let's look at that one more time in another way. We have 1, 2, 3, 4, and 5. And now we have the index positions as 0, 1, 2, 3, and 4, right? So now if the value is lying towards the left or towards the right, so in this particular case, our value, and the case we are discussing about is whether when we got 2 which we wanted to find out and 2 would have been less than 3, so in that particular case it would have been lying on the left position of the middle value. So our problem space is now reduced to the left portion, right? So now how do we represent the left portion? We represent the left portion with start equals to 0 and end equals to 1, right? And that is how, then that is why we were saying when the value would have been lying towards the left of the middle position, the end would move from here, which was initially it was pointing to this particular space, because the space has now been reduced to the left portion. So the end would be mid minus 1. And what is the index of mid? Mid index is 2 minus 1 is equal to 1. So that is where this space would have been represented as start 0 and end 1. So coming further to our previous example, the example that we started with for the value 5. So since 5 was greater than 3, so now in this iteration 2, what happens? We have got, and we have reduced this space to the right space, right? So the right space is this particular value over here, the right space. So the right space illustrates that our start is equal to mid plus 1. And what was mid? Mid was 2 over here. So start is equal to 3 and would remain as it is, which is equals to 4. the index. And now here we will again see what is the x of mid. But here, what is the mid value? First of all, so we have the start 3 and 4. So mid is equal to, let's recalculate it, integer of 3 plus 4 divided by 2, integer of 3.5 is equal to 3, right? So the x of mid is equal to x of the index 3, and at the third index, what we have the value 4. So now 5 and 4. So the value we need to find out is 5 and the middle value is 4. So how does 5 compare to 4? 5 is greater than 4. So then that means it is towards the right region of the middle, right? So we have the middle here at 4 right now. So our problem space at the beginning of this particular iteration was this, which is 4 and 5, which is the right portion of the previous middle value. And here we had the mid value was 4. This is the mid value, right? We have the mid value as 4, index 4, index 3, sorry, index 3, but the value was 4, right? And we have the end, which is pointing to this particular index, and we have a start, which is pointing to 3. So start is also here, right? So now we have this particular thing. So now what we are saying, since 5 is greater than 4, so we will, the problem space is towards the right of the number that we have, or right of the middle. So this is the right space, right? And for this particular right space, and basically since 5 is greater than 4, so our start will move to the mid plus 1. And what is the mid value? The index of the mid value is 3 plus 4 is equal to 4. So the start is equal to 4, which is here, and would remain the same, which is as the previous value, and is equal to 4. And what we have, the mid value again. The mid value is equal to, we calculate the mid value here now with the new start and end values. 4 plus 4 divided by 2 is equal to 4. So the mid would also point to index 4. So in this particular case, at the beginning of the third iteration, what we are having, we have start is equal to 4, end equals to 4, mid equals to 4. Essentially, the problem space is this, which every start, end, and mid are all pointing to. And we see our value 5, whether 5, how does it compare to the x of mid, and x of mid in this particular case is 4. So how does 5 compare to 4? 5 is, sorry, x of x at the fourth index position is 5. So how does 5 compares with 5? 5 is equal to 5, and hence at the mid position we found the element, right? So this is how the binary search algorithm works out. So at every iteration we saw that the problem space was reduced to half. So in this particular case, for length array of length 5, or the list of length 5, we took 3 iterations to determine the particular value, and it was lying at the end of the array over here. So this is the algorithm of binary search, and this is how the algorithm has been devised, and it is a very powerful algorithm with a time complexity of O log n, um, as compared to ON for the linear search algorithm. We will discuss about the time complexities in another session, but to give you an intuition, so if there would have been 10 to the or 2 to the power, let's say 22 elements in an array where n is equal to this, so the linear search would have taken 2 to the power 22 as the time complexity, or the growth pattern would be like this. But the binary search would have taken this, and we can write it as this, 22. So only 22 in the 22 would be the growth element. So compare 2 to the power 22 with just plain 22, right? It's huge. So now let's see how it is implemented in code. So let's implement the binary search in code. So this is the input for binary search would be a list X, and let's say the value we need to search out is a val, denoted by val parameter. And herein, first of all, what we need to do is let's take the length of the list. Right, so we have, let's say, the length of the list X we have taken, and then the start pointer we would be initializing it at 0th position, and the end counter would be the length minus 1, right? So that is the last index position of the last element of that particular list. And now what we need to do is, like, we will go in the loop while start is less than or equal to end. So now this is a very useful or very specific or very what we call is like a typical use case of while loop, because we know the end condition. The end condition is when the start would be the while it is less than or equal to end, that is when start gets greater than the end. Then what does that mean? That okay, the element is not found, or element it does not exist in that particular list. So this is the specific use case or the specific criteria which is there for ending this particular loop. And it is intuitive in a sense that okay, let's say if we would have found out the middle portion, the middle value, and our number is greater than that particular mid value, so we would have moved to the right space, right problem space, and in the right problem space again we would have got the middle value. We would have again moved to the right space and we keep on doing it, and till the end, when we saw in that example where start was equal to end as equal to the mid, that is equal to the last element. And if that would not have been 5, and let's say it would have been again a value 4, so then what we would have done is it would have moved it to more writer space, right? So the right of the last element, the start position would have moved by 1. So then that particular case, start would have been greater than the end, right? So this is an intuition wherein the start is less than equal to end is to be put in the while loop. And now what we do is basically we check whether, so we calculate the mid position. So what is mid? Mid is equal to integer, right? Integer of the start added with end and divided by 2, the middlemost position. And now here we check simply if the list, or sorry, if the val is equal to or is equal to the mid position of that particular list. If it is, then we say that okay, we have found the value, right? So herein what we will be putting it have found equals to true, and let's say we initialize the have found variable over here with a false binary value. So here we do not elif if it is not the case and val is basically greater than x of mid. So basically we are moving towards the right space because the value is greater than the middle position. And what we will do over here, to move it to the right space, we have to increment the start value to 1 plus the mid value. Else, so the only else condition, so what would go, like if val is basically less than x mid, then what we do is we basically move the end position because we are moving into the left space, so it is mid minus 1, right? So we do this way, and at the end what we do is basically we return the value have found to specify whether we have found this particular value or not. So okay, here basically when we find this particular value, we'll break out of this particular loop. All right, so this a simple implementation of the entire binary search algorithm. So let's try to run it and seek out whether it is giving us the right results. It's taking some time to connect. Okay, so now let's run this function. Okay, so now let's execute some test cases, binary search, and okay, first of all, let's define the list. So let's say the same example that we took 1, 2, 3, 5, and we took the val equals to 5, and when we do a binary search providing the value x and val, and let's see whether it is able to find out. Or here basically what we can also do is have a print statement so that we get to know how many iterations and what kind of iterations were those. Print, we can do in a string over here, the start is equal to start, and then we have end equals to end, and we have mid equals to mid, and let's say we also print out the element it currently it is comparing with, which is x of the mid. This has to come into the curly braces. Yeah, so let's rerun this function, and now let's run the algorithm. So we see that okay, in the first iteration it took 3 iterations. First of all, 1, 2, and 3. First iteration start was 0 and 4, which is the last element, which is the last element, index of the last element, mid is equal to 2, and element it compared was 3, right? This is the 3 middlemost value. And the second iteration, the start moved further because it was 5 is greater than 3, so it will be mid plus 1. So mid was 2 in the previous step, so start will be 3, and the end remains as it is, which is 4, and the mid again is recalculated. So start is 3, end is 4, 3 plus 4 is 7, 7 by 2 is 3.5, int of 3.5 is 3, and the element is 4th, and again 5 is greater than 4. So now it moves further in the third iteration, wherein it says start is equal to mid plus 1, which is 4, end is equal to 4, and mid also is equal to 4 because start plus end divided by 2, that is 4 plus 4 divided by 2 is 4, and mid is 5. So here it finds it equals and returns the value true. If we would have searched for 6, let's say, so after the 3 iterations, after the 3 iteration where the start becomes equals to end, in the next iteration what would happen is the start would be mid plus 1, that is 4 plus 1 is 5, so start would have become greater than the end, and hence this basically came out of the loop and it returned the initial value of have found variable, which is false. It wasn't able to find. So this is a simple implementation of the binary search, and this particular code can be found out, and I've basically a bit more enhanced this particular code for visual representation, which additional test cases, and you can find it out the GitHub, the link of which is given in the description of this particular video. I hope this was a useful video to understand binary search. Thank you for your patience. And this would be most beneficial if after going through this particular video, if you can basically try to depict the entire working on a pen and a paper, and let's see how much of it you are able to recall. Practice it for some more time. Do it for a couple of times, and this algorithm will be very near to you.